And we're going to go ahead and talk about our last two special segments and triangles. We talked about mid-segments, talked about altitude, and our median. Now we're going to talk about our bisectors. First, our perpendicular bisectors. Go ahead and highlight that so it sticks out. The perpendicular bisector, the two things that are important to remember about a perpendicular bisector are in the name. First, perpendicular, then bisector. So we're going to have a segment that is perpendicular. And as we discussed with altitude, you need to remember perpendicular forms a 90-degree angle. It's going to be very, very important. It'll be perpendicular to a side of the triangle and that side's midpoint. Important thing to understand, with median and with altitude, they had to come out of the vertex. Mid-segment had nothing to do with the vertices. With the perpendicular bisector, it does not have to pass through the vertex, but it can. Okay? So what we're going to do is draw our perpendicular bisector, hitting that midpoint M on these sides, segment PR on all three of these. We're going to see what ends up happening. So we start first, instead of starting at the vertex and going 90 degrees like we did with altitude, we're not necessarily going to go in the vertex. So we have to start at the midpoint, and we need to go straight up so that we can form our perpendicular 90-degree angle, perpendicular bisector. So that's where your two things come in. So you have your perpendicular 90-degree angles and your midpoint creating two congruent segments, cutting that side in half. Okay, if you look at it and you look back at your median altitude, I like to say this is if median and altitude had a baby, because you've got the median part, the midpoint, and you have the altitude, that 90-degree angle. Now we look at the next one, we're going to see this one's not going to go into the vertex, because if I go into the vertex, I'm going to be going slanted, and it won't create a 90-degree angle down here. That's why I said with perpendicular bisector, we start at the midpoint, and we move from there going straight up. Okay, so I want you to see how that happened. So we had that 90-degree angle, so we have perpendicular and bisector. Okay, and it doesn't go through the vertex on this one. Okay, and that's fine. The last one, again, we're starting directly at the midpoint, and we're just going to go straight up. Well, as straight up as we can, right? I didn't do such a great job on that. But here, to let everybody know, hey, this is a perpendicular bisector. We have our perpendicular part and our bisector part. So perpendicular bisector. With your perpendicular bisectors, they sometimes pass through the vertex, like we just discussed and saw. When we have this intersection of all three, because again, they will have three perpendicular bisectors, just like the altitude, median, and mid-segment. When they intersect, they could end up intersecting inside, outside, or on the triangle. Okay? Inside, outside, or on. And when they all three intersect, that point of concurrency, that point where they all intersect is called the circumcenter. Okay? This is where your three perpendicular bisectors intersect. So with our picture here, we're going to make sure that we have all three perpendicular bisectors marked with our perpendicular and bisector part. So if we start with this one first, I'm going to rotate it this way. So we have our bottom right here. We have perpendicular, and then we have bisector. Okay? Rotate it around. Here, we have perpendicular, and then we have bisector. Remember, we have to put two tick marks now, because we need to tell the difference between these two segments and the first two. Rotate it around, and here we have our perpendicular and then bisector. All three parts. Two words, two things we need labeled. Okay? And then at that where all three of them intersect, in this case, that is going to be, the intersection is going to be inside. This right here is our circumcenter. Okay. Now there is something else we need to know about a perpendicular bisector, and it's the theorem. What happens is it states that if a point on the perpendicular bisector of a segment, if you have a point that's on that perpendicular bisector, so any point on this perpendicular bisector, it is going to be equidistant from the endpoints of the segment. That sounds confusing, right? Well, let's take a look at this. Equidistant, equal distance. So here we see that if C right here, this is a point that's going to be on this perpendicular bisector. All right, ignoring the fact we have a triangle, we just have segment AB. It's a perpendicular bisector of just segment AB. So it's going to cut through at the midpoint of AB, creating two congruent segments, AP and PB. What's happening here is we're going to have a point on this perpendicular bisector, which is point C right here. And when it says from the endpoints of the segment, what we mean is this point, the distance from C to A, the endpoint of AB, and C to B, the other endpoint of AB, they are going to be congruent. Okay? So you have an isosceles triangle. All right? And that's what ends up happening with perpendicular bisector. When it comes out of the vertex, you actually have an isosceles triangle. Okay? So let's take a look at this in action here. We just want to find x, that is it. So we're only solving for x, no substitution. Here I see that I have a perpendicular bisector because I have the perpendicular part and I have the bisector part. So this point right here, U, is going to be the exact same distance from T as it is from V. That's your perpendicular bisector theorem. So this side and this side, TU and VU, are congruent. And when two sides are congruent, their measurements are equal. So we're going to set these equal to each other. We have 3x plus 9 is equal to 7x minus 17. Going through our process of solving for x, I'm going to move that 3x first, cancel it out. I'll move the variable with the smaller coefficient. Bring down 9 equals. We have 4x's left over. Bring down your minus 17. Then we got our variables to one side. Let's get our constants to the other. So 17's canceled. All that's left is that 4x. And 9 plus 17 is going to give me 26. Last step, divide by that 4. Looks like I'm running out of room. So 26 divided by 4 will not be a whole number. We are going to have a decimal, but it's a nice decimal. It's going to end up being 6.5. So 6.5 equals x. Or if you're going to write x equals 6.5, that will do as well. Next, our last special segment, our other bisector, our angle bisector. Angle bisector is not new. We talked about angle bisector without the triangle part of it. Now we're dealing with the triangle. So here we're going to have a segment that bisects one of the angles of a triangle. Okay? So let's go ahead and draw on our triangle. And we're going to draw that angle bisector. It's going to come out of a vertex. It has to. We'll talk about that in a minute. Because if it's bisecting an angle, it has to come out of the angle, which is the vertex. And we're just going to eyeball it. But we're going to let everybody know this is an angle bisector because we're going to put those congruent arcs in there. So now we've cut that vertex into two congruent angles. Your angle bisectors, they always have a vertex as one endpoint. Okay? Just like your median, just like your altitude. And they're always going to intersect inside of the triangle. And when these three angle bisectors, because each one of these, all 5 of these special segments have 3, because we have 3 sides of a triangle and 3 angles of a triangle, when all 3 of them intersect, you will get the incenter. This is the 3 angle bisectors intersecting. And your incenter is equidistant, same distance from the 3 sides of the triangle. Okay, and we'll take a look at what that means. All right. So with each one of these, we need to make sure that we see an angle bisector first. So I'm going to take this first angle bisector right here, and I'm going to go up to the angle, and I'm going to mark congruent arcs, saying I have 2 congruent angles. Now it is an angle bisector. When I go to the next angle, or next angle bisector here, I need to go up to that vertex, and just like the tick marks, we can't do just one arc. We're going to have to add in an additional one. Okay, saying that those 2 are congruent to each other, but not the other ones. And then our last angle bisector here, we need to put 3 arcs. So here are 3 angle bisectors. And then we have this point of concurrency where all 3 intersect, and this is our incenter. Now, we talked about that the incenter is equidistant, same distance from each of the 3 sides. What that means is we go to the incenter and we go down the angle bisector to each side, not the angles, but the side. So I want you guys to see what I'm pointing at right here, what I'm tracing. Each one of these segments are equidistant, they're congruent because this incenter is the same distance from all 3 sides. So all 3 of these are congruent, not the ones that go to the angles, the ones that go to the sides. And of course you have your theorem. Your angle bisector theorem is saying we're just looking at angle bisector, not your triangle. So right now we're not looking at here or here. We're just looking at angle BAC, and angle right AD is going to be the bisector. If we have a point that lies on the angle bisector, then that point, just like when we did the perpendicular bisector, is going to be equidistant, and it's going to be equidistant from the sides of the angle. So what that means, like I told you here, we have ray AD bisects angle BAC, okay? And what also ends up happening here is that point D that's on that bisector, it's going to be perpendicular with each side, and when you see the angle bisector and you see these perpendicular markings, then that point D is going to be equidistant, so we're going to have the length of BD and the length of DC are going to be congruent. Okay, so these are the markings we need to get used to. And you could also have the converse of it. I might give you these markings, and you have to know the angles are congruent. So let's take a look at our 2 examples. We want to find the measure of angle EFH, so E to F to H, just this little angle right here. Given that angle EFG, the whole thing here is 50 degrees. Well, because I see these 2 tick marks right here, this is telling me, this is the opposite of what we just looked at. I'm telling you that this point H on this ray is the same distance to each side of that angle. And I see that perpendicular marking and I see the congruence, so automatically these angles are going to be congruent. So if the whole entire thing is 50 degrees, we can determine here that the measure of angle EFH, what we're looking for, is going to be half the measure of the entire angle EFG, because angle bisector cut it in half. So we have 1/2 of that 50 degrees, concluding the measure of angle EFH is equal to 25 degrees. All depending on what information they give you. They gave us the whole angle. We needed to cut it in half because it was a bisector. The next one, we're just going to find x. Okay, we're being told that here BD, so here to here, is 3x minus 4, and we're told that DC is x plus 8. What I see in the picture are the angle being bisected, so we have an angle bisector, and that point D, when it meets up with each side of that angle, it forms that perpendicular 90-degree angle. These are hints here that we have our angle bisector theorem, so BD is congruent to CD. So the length of BD will be equal to the length of CD. So since they are congruent, we set them equal to each other. So we have that 3x minus 4 equal to x plus 8. Solving for x, move our variable first. Let's go ahead and move that x over to the left. So we're going to subtract an x from each side. We get 2x minus 4. And bring down that, it is a positive 8, so we're going to just bring down an 8. Next, our variables went to the left. We need to get that constant, that negative 4, to the right. So we're going to get rid of it by adding 4. We bring down our 2x. We're going to set that equal to 8 plus 4 will give us 12. Now, time to get rid of that coefficient, divide both sides by that 2. And x, our final answer, is going to be equal to 6. And there are all of your special segments.